This is what the inside of a lithium-ion battery looks like.
It's not exactly high-tech, just 2 meters of foil coated in black paste, all packed into this tiny 45-gram cylinder.
But these are some of the best batteries we have. They power everything from laptops and electric vehicles to orbiting satellites.
Yet when a battery fails, all that energy can get released in the wrong way.
So how did something so rudimentary looking end up in almost every electronic device on the planet? And why don't we have anything better?
In the early 1980s, most rechargeable batteries were stuck at just 40 to 60 watt-hours per kilogram, meaning you would need a kilogram of battery to power a 40-watt light bulb for just an hour. As a result, when the first commercial mobile phone launched in 1983, it was pretty unimpressive. It took 10 hours to charge for just 30 minutes of talk time. Laptops, cameras, even medical devices all suffered from the same bulky batteries. Everyone from electronics giants to oil companies were trying to make a better battery because they knew that even just doubling the energy density could unlock a new era of portable electronics and power the digital revolution.
But what no one realized is that someone had already found the solution.
In 1972, a 32-year-old British chemist named Stanley Whittingham was studying how different materials store energy at Exxon's research lab in New Jersey. Yes, that Exxon, the multinational oil giant, then the largest oil company in the world, they were researching batteries.
Up until the early 1970s, just about every commercial battery used a water-based electrolyte. And as a result, none of these battery cells could push much beyond the 1.23 volt limit. Now, the total energy a battery can store depends on how much energy each charge has to give, times how much charge can move. That is, the battery's voltage times its capacity. So if you can't increase the voltage, your only option is to make more battery, more cells or bigger cells. But that won't increase the energy density.
And this is exactly the problem Whittingham was trying to solve. He was searching for materials that could store large amounts of energy in a compact space with light weight. That led him to a class of compounds called transition metal dichalcogenides. He zeroed in on one in particular, titanium disulfide. Titanium in this compound has effectively lost 4 electrons, 2 to each sulfur atom, meaning it sits at a +4 oxidation state. That leaves it very electron hungry, exactly what you want in a battery cathode. But titanium disulfide has a second key advantage. This material is made of stacked layers held together by weak van der Waals forces. This creates natural gaps between sheets of titanium and sulfur atoms just wide enough to let certain ions slip between the layers, a process known as intercalation. Better still, the structure can expand and contract repeatedly without breaking down. Now Whittingham just had to decide which ions to use. He initially looked at potassium, but it was just too reactive and far too dangerous to work with.
Oh, yeah!
He turned to this, a soft, silvery metal called lithium.
What makes lithium unique is not the fact that it has one electron in its outer shell that it wants to get rid of, no, that it shares with the other elements in its group. What sets it apart is how much energy you can get out of lithium when it reacts in a battery. See, when it loses that outer electron, it forms a tiny, incredibly stable positive ion. And so that reaction, paired with the right cathode, releases more energy per electron than any other metal. That's why it produces the highest voltage of any metal used in batteries. And because it's so small, with just 3 protons, lithium is also the least dense metal at just 0.53 grams per cubic centimeter.
This combination of low density and the tendency to give away its electron made lithium perfect for Whittingham's vision of this high energy density battery. But while lithium was easier to work with than potassium, easier still didn't mean easy. Here's what happens to lithium if you put it in a glass of water. Safe to say you don't want this happening inside your battery.
So Whittingham had to switch out the water-based electrolyte for something else. And that change unlocked the possibility of higher voltages. He turned to a solution of lithium salt in an organic solvent, and it worked. But it came with serious risks.
The solvent was volatile, the lithium salt was chemically unstable. Together they formed a mixture that could explode or release toxic fumes if mishandled. everything had to be done with extreme caution. A stray spark or a trace of moisture could destroy the experiment or start a fire. But if you could get around the danger, this new electrolyte was a huge perk.
It let lithium ions shuttle between electrodes without breaking down the solvent or the cell, at least not until much higher voltages. Whittingham had unlocked lithium's potential, and in the process, he'd broken through the 1.23 volt ceiling. His new chemistry delivered nearly double, a huge 2.4 volts per cell.
He now had a working prototype, a metallic lithium anode on one side, a titanium disulfide cathode on the other. In the winter of 1973, Exxon's managers summoned Whittingham to the company's New York office. Whittingham later said, "I went in there and explained it. 5 minutes, 10 minutes at the most. And within a week, they said yes, they wanted to invest in this." They got to work at the Exxon laboratory, but it wasn't all smooth sailing. Firefighters had to be called out repeatedly. They were called so often they threatened to start charging the lab for the special chemicals needed to extinguish the burning lithium.
The problem was the anode. Whittingham's design used pure lithium, which worked brilliantly until it didn't.
We've made a special cell. We made a transparent battery.
So cool.
But they're very, very small, so we have a microscope lens just to allow us to see it. What you're seeing here is a piece of copper which we're gradually plating with lithium. So this is analogous to the first generation lithium metal batteries, which use lithium metal as the anode. On this side, we have a piece of lithium. As we charge the battery, we're stripping the lithium from that electrode and we're plating it. And actually what's happening right now is the ideal reaction, where it's very slow, we're getting a dense plate. The challenge then becomes if we go too fast.
Oh, that is huge.
Everything's fine until all of a sudden it's not fine. So we want the lithium to plate evenly across everywhere, but instead it forms in that one location. And that is what is a lithium dendrite. That lithium dendrite can grow. The length scales of this is on the order of millimeters. So that would have easily short-circuited the battery.
And that dendrite can just keep growing, and eventually it's going to poke through the separator and reach to the other side. Now the electrons are going to have a shortcut, so instead of going through the circuit, they race straight from the anode to the cathode using the dendrite. And that sudden surge of electrons cause intense heating, and that can trigger a chain reaction inside the battery, leading to a fire or even an explosion.
For all its promise, Whittingham's battery was just too dangerous. And then the oil crisis ended. Prices dropped, and Exxon's urgency evaporated. The company shut down its lithium battery program. Whittingham published his design in 1976, and Exxon licensed the patent to a few manufacturers. But with no funding and no momentum, the first lithium battery revolution died before it had a chance to take off. Fortunately, a copy of Whittingham's paper made it across the Atlantic to Oxford University in England, where it caught the attention of John B. Goodenough, an American physicist leading a solid-state chemistry group. As he read the paper, one thing stood out. The cell voltage was being held back. The material Whittingham chose for the cathode, titanium disulfide, capped the cell at just 2.4 volts. But Goodenough believed that with a better cathode material, he could do better. He had previously worked with compounds called transition metal oxides. They were more stable than sulfides, and some, he knew, were extremely hungry for electrons, perfect for a cathode. He tried one of these compounds in his battery, and the voltage immediately spiked from 2.4 volts to 4 volts. This jump was incredible.
But what was even more surprising was the fact that this compound already had lithium in it. The material was lithium cobalt oxide.
Lithium cobalt oxide is arranged so that the cobalt and oxygen atoms form tightly bonded layers, with lithium ions nestled in between. This means that your supply of lithium ions doesn't just have to come from the dangerous lithium metal on the anode side, it's already there, pre-built into the cathode. So theoretically, you don't even need lithium metal at all. You could assemble the cell in a discharged state with all your lithium ions in the cathode. Then when you connect it to a charger, these ions will get expelled from the cathode crystal lattice and into the electrolyte. At the same time, nearby cobalt atoms will give up an electron to balance out the charge, and those electrons then go through the wire to the anode to meet with the ions. If Goodenough could find an anode that would replace lithium metal, the battery would become safe enough to leave the lab and actually power real-world devices.
So, he took it to a government lab near Oxford, the Atomic Energy Research Establishment. They agreed to fund the patent, but only if Goodenough signed away his financial rights. Now, this should have been a gold mine, but the lab didn't realize what they had.
And so for the second time, the lithium battery revolution was boxed up and shelved. While Goodenough's battery design was gathering dust, 10,000 kilometers away in Japan, a 34-year-old chemist named Akira Yoshino was trying to find a safer battery anode, one that didn't require lithium metal. Yoshino was actually looking at plastic. Now, normally plastic is an insulator, but the kind Yoshino was looking at is different. It's called polyacetylene, and its carbon atoms are arranged in a repeating chain of single and double bonds, a structure that gives it unusual electronic properties. So the plastic conducts electricity like a metal. And that got Yoshino thinking, what if polyacetylene could work as a battery anode?
During charging, it could absorb lithium ions and electrons, and then during discharge, it would give up those electrons to the circuit, just like lithium metal does. If it worked, it could eliminate the most dangerous part of the battery, the metallic lithium.
But for months, Yoshino struggled. Obviously, since he removed lithium metal from the anode, he had to get lithium ions from somewhere else, and he couldn't figure it out. And then, just as he was losing hope, he stumbled upon a 1980 paper by John B. Goodenough. It described a cathode made of lithium cobalt oxide, a cathode that already contained lithium. This was the missing piece.
He sketched out the reaction between lithium cobalt oxide and his lithium-free anode, and then built a test cell using the two materials. It worked, safely and reliably. But Yoshino wasn't satisfied. The material he used for the anode, the polyacetylene, had an extremely low density. It couldn't pack in enough lithium, so the energy density of the battery was terrible.
Yoshino needed something more lightweight, compact, conductive, and crucially, something that could reversibly accept and release lithium ions within its structure without breaking down. A breakthrough came from within his own company. Another team had developed a new form of carbon with a unique crystalline structure. They called it vapor-grown carbon fiber. He got his hands on a sample, tried it in the lab, and it worked. Later, Yoshino would say, that was the moment when the lithium-ion battery was born.
But his employer, Asahi Chemical, well, they weren't a battery company, and they didn't know how to make batteries.
So in 1986, Asahi executive Isao Kurabayashi flew to Boston on a top-secret mission, carrying 3 jars containing cathode, anode, and electrolyte materials. He handed them to a tiny firm called Battery Engineering, working out of a converted truck garage, and he asked them to turn the materials into cylindrical cells like the kind you might buy for a flashlight. The team did just that, completely unaware of what they were handling. It wasn't until 2020 that employees learned the truth, that they had helped assemble the world's first pre-production lithium-ion batteries. 2 weeks later, Kurabayashi returned to Japan with 200 finished, perfectly functioning cells.
Even then, Asahi's leadership hesitated.
Kurabayashi refused to give up. On the 21st of January 1987, he visited Sony, and he took one of the prototype cells and rolled it across the conference table to the Sony execs. And at last, they saw its potential. They reworked the design, swapping out Yoshino's carbon material for graphite that could better intercalate lithium ions between its layers. And in 1991, Sony launched the first commercial lithium-ion battery inside this,
the Sony Handycam.
Their battery was compact, rechargeable, powerful, and crucially, free of unstable lithium metal. It was Sony who first coined the name lithium-ion, and it stuck. But this wasn't just about one camcorder. Competing companies like Panasonic and Sanyo raced to catch up. Lithium-ion batteries started appearing in phones, CD players, laptops. Manufacturers actually began to advertise the use of lithium-ion batteries as a key selling point of their products. But what's crazy is that even after all this, these batteries should never have worked. See, when you charge the battery for the first time, lithium ions move from the cathode to the graphite anode. And here, they react with the electrolyte to form this weird, complex patchwork of compounds that build up on the anode surface. These parasitic side reactions should keep going on indefinitely, using up all the lithium and destroying the cell. But they don't. Instead, they form a thin protective layer known as the solid electrolyte interface, or SEI. It's a kind of chemical shield protecting both the graphite anode and the electrolyte from further reactions. But crucially, lithium ions can still slip through it.
When the SEI originally forms, during the first charging cycle, around 5% of the lithium in the cell actually gets stuck in this layer, decreasing the battery's capacity. But this little trade-off is what makes the battery stable enough to be used for years or even decades, which is why today, lithium-ion batteries are virtually everywhere.
From 1991 to 2023, the price per kilowatt hour dropped by 99%, from nearly $9,000 to just $100. At the same time, energy density and cycle life, how many times a battery can be charged and discharged before it wears out, improved dramatically, crossing a critical threshold. Lithium-ion batteries had become powerful enough and finally cheap enough for something bigger: the return of the electric car.
Today, lithium-ion powers a $100 billion industry. In 2019, Whittingham, Goodenough, and Yoshino finally received the Nobel Prize in Chemistry for an invention that, in the committee's words, revolutionized our way of life. This made Goodenough the oldest Nobel laureate in history, receiving the award at the age of 97.